Hey folks, my name is Nathan Johnston. Welcome to lecture 21 of vector calculus, which, just like the previous video, is all about path-independent line integrals. But what we're going to do in this video is we're going to do two things. We're going to write down exactly which vector fields have path-independent line integrals, and also we're going to come up with a formula for those path-independent line integrals that depends only on the endpoints of the curve that you're integrating over. Which makes sense because if the line integral is path independent, it doesn't matter how you get from A to B. Well, there should be a formula that just depends on those 2 points A and B. And there is, and we're going to see what that is today. Okay, so let's dive in and see the main theorem that's going to do all of the work for us today. Okay, and we sort of hinted at pieces of this in the previous video, but let's write it down explicitly now. Okay, so here's the setup. We have some vector field in front of us. It's acting on some domain X, which is in n-dimensional space. Okay, and we got a vector field. It's continuous, and we want to know, does it have path-independent line integrals? Okay, well, it turns out f having path-independent line integrals, that's exactly equivalent to, well, if you integrate around any simple closed curve, well, then you're going to get 0, which, again, like this should make intuitive sense. If it has path-independent line integrals, then integrating around a closed curve is just the same as integrating like at the dot, not moving at all. So you should get an integral of 0 there. And this theorem's just saying, yeah, that's the same thing. Okay, and that's also equivalent to, well, your vector field being a gradient field. That's equivalent to your vector field being the gradient of some C1 scalar field acting on the same domain, okay? And we already know from previous videos, how do you tell whether or not your vector field is a gradient field? Well, you can sort of integrate term by term or check sort of the mixed second partial derivatives, equality of those. We've already talked about those previously, so this gives us a nice concrete way of checking whether or not our vector field is a gradient field, okay? All right, so great. Okay, furthermore, not just, yeah, it has path-independent line integrals if and only if it's a gradient field, but also in this case, when it is a gradient field, so the line integrals are path-independent, furthermore, there's a nice formula for those line integrals, okay? The line integrals, they're just equal to the potential function at B minus the potential function at A. In other words, like if your curve that you're integrating is going from A to B, then your line integral doesn't depend on any of the inside stuff, okay? It only depends on f at b and f at a, and you subtract those, you get your value of the line integral, okay? All right, so let's talk about this theorem a little bit. It's a big beast of a theorem, so let's talk about some parts of it. In particular, we have some restrictions on the domain here that we haven't really seen before, okay? We've maybe talked a little bit about connectedness, but we haven't talked about openness, what that means at all earlier in this course. So let's talk about what the heck does it mean for a domain to be open? Okay, and what we mean by that is, like, if you pick any point in the set, if I pick any point, then there's some tiny little ball around it that's contained entirely in the set. Okay, so that's sort of what's going on over here. I picked some point in the set, there's a tiny little ball around it. And that's got to be true no matter which point you pick, no matter how close to the boundary it is, you can still squeeze in a tiny little ball around it. In other words, every single point in the set has to have a little bit of wiggle room on all sides around it. Okay, so sort of the intuition here is it doesn't include the boundary. There's nothing on the boundary of the set. If that's the case, then it's what we call an open set. Okay, we also said that the set has to be connected, which for open sets, what this means is that if I pick any 2 points inside the set, well, I can draw some curve that has endpoints at those 2 points, and that curve's contained entirely in the set. In other words, like sort of intuitively, like I could imagine like drawing a line with my pencil or my pen, and I can connect those 2 points, any 2 points, without lifting my pencil and without leaving the set. That's what it means for the set here to be connected. Okay. And finally, like this theorem up here, it has this nice little formula at the bottom here. Sometimes that formula is stated as a theorem all on its own, and it's called the fundamental theorem of line integrals, okay? And really, it is a direct generalization of the fundamental theorem of calculus for functions of one variable that you're already familiar with, right? You can think of this as like, oh, I'm integrating the derivative of a function, and what I get is, well, f at one endpoint minus f at the other endpoint. And if your function little f here happens to be a function of one variable, then that's exactly what's happening here. If n equals 1, this is literally just the fundamental theorem of calculus that you learned in first year calculus back in the day. Okay, let's talk a little bit about where this formula here comes from, and then we'll do a bunch of computational examples. Okay, so where's this formula here come from? You can come up with this formula based just on tools that you've already seen earlier. Okay, so if I wanted to compute this vector line integral, in other words, if my vector field is a gradient field, then what happens? Okay, well, my vector line integral, just by my standard formula for vector line integrals, it's, okay, integrate the vector field with the path plugged in, dot with the velocity vector, okay, and my vector field just happens to be a gradient field here. Okay, and now the trick is this thing on the inside, we've seen this. Actually, we saw this even before this course. We saw this back in multivariable calculus, not just vector calculus. This thing on the inside here, this, by the chain rule, this just equals the usual one variable derivative of the function f of x of t. Remember, like this f of x of t here, this is a function just of one variable. It takes one variable in, spits one variable out. It's a real valued function, right? It's taking in t and it's spitting out the scalar f of x of t. So it makes sense to talk about just the usual derivative in like the first year calculus sense. Okay, and the chain rule from multivariable calculus tells you that, yeah, the derivative of this thing, it's the dot product of the gradient with, what we're calling in this course the velocity vector. In other words, it's like the partial derivative of f with respect to x1 times the derivative of x1 with respect to t, and then plus partial derivative of f with respect to x2 times the derivative of x2 with respect to t, and so on, and add them up, and that's the same as doing a dot product here. Okay, so this is just the multivariable calculus chain rule. And now, like, all I've got is, like, this is a type of integral that you might have seen in first year calculus. Okay, I'm integrating with respect to t the derivative of a scalar function with respect to t. Oh, regular good old-fashioned fundamental theorem of calculus tells me that that had better equal, well, this function f of x with the endpoints plugged in, right? With b plugged in on one side and a plugged in on the other side, and you just subtract. And the point is, like, when I plug little b into the path x, I get one of the endpoints of the curve that path traces out. And when I plug little a into this path x, I get the other endpoint of the curve that path traces out, right? Like t is going from a to b. So like if I plug in a and I plug in b, those are the start and endpoints of the curve respectively. So those are what I'm calling big A and big B here, okay? So I'm just gonna make that substitution so that we get exactly the statement of the theorem that we had up here. Okay, so that's all that's happening. It's a combination of the chain rule and fundamental theorem of calculus. Okay, one thing that I want to say, just sort of on a terminology note before we go on to computational examples, is that here I made a little note that, a gradient field, sometimes people call it a conservative vector field. And we're going to be doing that more and more now. Okay, it's just new terminology. There's no new math here in any sense or anything like that. It's just whenever you see conservative vector field, just make the mental substitution. Oh, that means gradient field. Okay. Alrighty, let's go on and do some computational examples. All right, let's see how we can make use of this theorem here. Okay, so let's compute this vector line integral, where c is the curve traced out by some horrific path, where t is going between 0 and 2 pi. Okay, so now whenever I see a vector line integral, particularly one that has an awful path that I don't want to integrate over, the first thing I'm going to do is I'm going to ask myself, is that a gradient field? Is it a conservative vector field, and therefore have path independent line integrals, and therefore I can just plug in endpoints and get my answer? And in this particular case, I mean, it turns out, yeah, it is. We don't want to do it directly, okay? There's a better way, and yeah, it is. It's by observing that this vector field, oh, it's the gradient of this scalar field here. And I mean, this one's simply enough that you could probably eyeball that. If you aren't able to eyeball that, you can do the check based on the mixed second partial derivatives, or you can integrate, the first entry with respect to x, the second entry with respect to y. We talked about that a few videos ago. Okay, so yeah, it's a gradient field. Great, life gets so much easier. Okay, so my vector line integral, it's potential function at the right endpoint minus potential function at the left endpoint, or maybe more accurately, the terminal point minus the initial point. Okay, so I've got to figure out what those are. What's big B? What's the endpoint? What's big A? That's the initial point. And I just scroll back up, like, where's my curve going between? Okay, my path is going from 0 to 2 pi, so I just plug 0 and 2 pi into my path, and that'll give me my big A and my big B. Those give me my start and my endpoints. Okay, so that's all I'm doing over here. Plug in t equals 0, I get 0, 0 in my path here. If I plug 0 into that, I get 0, 0. Whereas if I plug 2 pi into this, I get 4 pi, 2 pi. Okay, so that's my terminal point. That's the end point of the curve. And now I can just take these and plug them in over here, and I'm going to get my answer. Okay, so it's potential function at the endpoint minus potential function at the initial point. And if I just scroll back up, what's my potential function? Yeah, it's right up here. Just plug those in, right? I'm plugging 4 pi in for x, 2 pi in for y, and then subtracting off when I plug 0 in for x, 0 in for y, and I just end up with 10 pi squared altogether. That's the value of the vector line integral, and I barely needed to use the path at all. It doesn't matter how hideous the path is, because all you need are the endpoints, as long as your vector field is conservative, as long as it's a gradient field, okay? All right, let's ramp up a little bit. Let's do a more complicated example, okay? Let's compute the vector line integral of this admittedly quite hideous vector field acting on three-dimensional space this time, okay? Where C is the helix traced out, by this path where T is going from 0 to 5 pi over 2. Okay, so I would love it if that were a conservative vector field, because again, that would make my life so much easier, okay? So yeah, first question you ask, is F conservative? And so you can go through like the mixed partial derivatives test if you want, or you can integrate term by term if you want. We're going to do the integration term by term thing, and it's going to turn out that it's not quite conservative, unfortunately. This is not a gradient field. Okay, let's see what happens. Okay, if I integrate the first entry, what I'm calling F1 here, if I integrate that with respect to x, I get this thing here. And remember, I've got a constant function of y and z left over because, I'm only integrating with respect to x. I'm keeping y and z constants here. Okay, so the weird y and z stuff can still be happening over here. I don't know, but as long as there's no x's in this piece, I'm fine. Okay, and then I integrate the second component, what I'm calling F2, with respect to y, and I get this thing. Integrate the third component with respect to z. Okay, and then I get this thing, okay? And each time I have a different constant function depending on, well, all of the variables that I didn't just integrate with respect to, okay? And if this were conservative, if it were a gradient field, then I'd be able to choose a g, an h, and a k so that all three of these were equal to each other. And I mean, they're almost equal to each other. Like, holy cow, there's a lot of terms in common, right? This xe to the yz's in common, this xz, and I could put an xz in here, so that term's fine. There's a y squared z, and I could throw a y squared z in there, that's fine. Oh shoot, there's a problematic term right here. There's got to be an xyz term in all three of these, but there's no way to work an xyz term in up here because I can't put an xyz in this term. Only things that depend just on y and z, no x's. Okay, so it's not a conservative vector field. There is no potential function little f that gives rise to this vector field. But the fact that it's so close to being a conservative vector field gives me a little bit of hope that maybe they can still help me here. Why don't I define a potential function that's not going to be quite a potential function for this vector field, but it will be a potential function for sort of most of the pieces of it. Like it'll give me this term and the xz and the y squared z. Okay, so why don't I define a potential function like this? I say, okay, little f, how about it's this thing here? Okay, because when I take partial derivatives of this, it's going to give me this term and this term and this term and this term and this one. The only term it doesn't give me is this x, y, z here. Okay, so what happens is the the vector field big F that I care about, that I'm trying to integrate, it's the gradient of this little f here, plus sort of a correction term, plus just a little bit more, plus this xy over here that unfortunately I couldn't get from the gradient stuff. Okay, then, yeah, I mean, this is a true statement, okay? And the point, like the reason this is going to help me is now if I want to integrate big F, well, I can integrate this and add them up. And this, well, it's going to have path independent line integrals. And this is a heck of a lot easier to work with than this. So it's probably going to be a lot easier to compute the integral of. Okay, so let's do that. Let's split the actual integral that I'm trying to compute into a sum of two integrals over these two vector fields. Okay, so yeah, vector line integral I care about is this vector line integral plus this one. Just add up the line integrals over the two vector fields. And the point is, well, this one has path independent line integrals, so I can do what I always do, plug in the two endpoints and subtract, right? This is f of big B minus f of big A. And all I've done here is I plugged the t endpoints into my path, right? Okay, so t equals 5 pi over 2. Plug that into the path, and you're going to get 0, 1, 5 pi over 2. Plug the left endpoint in, plug 0 into this path, and you're going to get 1, 0, 0. And that's just f of those two endpoints. Subtract, and this, whatever this is, will equal this first vector line integral here. Okay, for the second one, I don't have any shortcuts, but that's okay. The vector field's not too bad. So I just plug into the formula for how you compute vector line integrals, right? So over here, I've got big F of the path. Okay, so I'm going to go back up to my path. Okay, x is cos t, y is sine t. I plug those in here, and I get 0, 0, cos t sine t. Okay, so this is f of x of t. Here is x prime of t. It's the velocity vector, right? Because that's how you compute vector line integrals. It's f of x of t dotted with the velocity vector. So I just went back up here, took the derivative entry-wise of my path, and I got this thing here. Okay, and now I just compute all this crap. Okay, now I'm at the stage I can just plug everything in. Okay, my scalar field, my potential function with 0, 1, 5 pi over 2 plugged into it is 5 pi over 2 minus that scalar field with 1, 1, 0 plugged into it is this 1. So now I get 5 pi over 2 minus 1, and I've still got plus this integral left over, so the integral of cos t sine t from 0 to 5 pi over 2. Well, the indefinite integral of this is sine squared over 2. And you just plug stuff in, and you end up getting 5 pi over 2 minus a half as your final answer for the value of that vector line integral, okay? And we could have tried doing this directly, right? We could have tried doing this a couple weeks ago before we knew anything about path-independent line integrals, but it would be an absolute nightmare, right? Because you're plugging this junk in to this vector field, so you're gonna have terms like e to the yz. That's an e to the sine t times t, and then plus another z, and then like here you've got an xz, well that's t times cos t times e to the sine t. Like, holy cow, I don't want to integrate that. Path independent vector line integral saved us, even though that vector field wasn't quite path independent. Okay, it was sort of close enough that we could leech off of it. All right, and we'll leave it there for this time. So thanks for watching, everyone. I will see you in a couple more days.